We shall continue with our discussion on SQL. As we mentioned in the previous classes, SQL is a language, a commercial language, which is capable of defining a database, and it has got a data manipulation language or a query processor in which you can provide queries specified in a particular syntax. The syntax of a SQL query is of the following form: select A1, A2, A3, where from R1, R2, where a predicate P must be satisfied. This is the format, and we will quickly revise the types of queries that we did till now before going into the other features of SQL. The simplest query is of this type: select title from book, which is equivalent to this query in this statement in relational algebra. In book, you project out all the titles. Select all title from book. This all, if it is there, then non-duplicate items, even duplicate items will be listed even if it exists more than once. And distinct will remove all duplicates. This query, select accession number, year of publication from book, where title is equal to compiler design, is equivalent to project out accession number and year of publication from book after selecting out title equal to compiler design. So these two attributes will be there in the final relation which is returned from the relation book, where title is equal to compiler design. These are all attributes of the relation book. We did natural join in this way. Select card number from book, comma borrow, where book.accession number is equal to borrow.accession number. Now book and borrow have got only accession number as the common attribute, and therefore we have to explicitly equalize the common attribute if we want to do a natural join. That is, in SQL, normally whenever we write down these two relations, it is a Cartesian product of these two relations. Therefore, this is equivalent to pi out of card number from book natural join borrow. We discussed the use of variables when we solve the problem. Find out the names of all borrowers who have the same address as Vijay. This name and address of Vijay was available in the user relation. Now in the user relation, we have to use the user relation twice. So we do a Cartesian product of that, and to rename it, we use the tuple variables or the variables t and s. And we solve the problem by saying select t dot borrower's name from user t and user s, where s dot borrower's name is Vijay and t dot borrower's address is equal to s dot borrower's address. This is how we solve the problem of renaming and using the same, doing a Cartesian product on the same relation. We found that SQL provides a number of set operations which are there, some of which are directly there in relational algebra and some of which are not there, but they are more useful when we provide them in SQL. For example, here we had the example select accession number from book where title equal to compiler design, intersection select accession number from borrow. This will do an intersection of these two, though in this particular case it will only give, since all the books are there in the book relation, therefore intersection of these two will give you the accession number of all the books which have been borrowed and whose title is compiler design. Other than intersection, we have minus and union. And in this particular case, when we do union, intersection or difference, which is minus, and this situation, the attributes of the two relations must be identical. Otherwise, this set operation is not applicable. We saw some other additional set operations, one of which was the in operation. And in this particular case, we saw it is select card number from borrow, where accession number is in, that is, it is an element of this set, where this set is defined to be select accession number from book where title is compiler design. This will give you the accession number of all books which are compiler design. This will give you card number from borrow such that the accession number is in this set. Together, this query will give you the card number of those people who have borrowed a book related to compiler design. Other than this in, we had the all or the sum operation. In this particular example, select price from the sub relation where S name, that is supplier's name, is Narosa and price is greater than all of this set. Now this set must return only price. Therefore, price must be greater than equal to, this is the price, select price from sub where S name is Narosa. So this returns the price of all books supplied by Narosa. And if we say select price from sub where S name is equal to Narosa and price is greater than all this, then we will get the largest price book supplied by Narosa. Other than all, we can also have sum, which will give you whether there exists. Now, and this relation can be greater than equal to, less than equal to, not equal to, greater than or less than. And finally, we saw two other operations. One is the subset relation, which had the contains operation. And in this particular problem, we solved the problem of find out the names of all suppliers such that they have supplied titles corresponding to all the books issued by Vijay. So in this particular case, this one which is marked out, we have found out the titles of all the books issued by Vijay. How did we do that? Select title from book user borrow, and we did a natural join of book user and borrow by where book.accession number is borrow.accession number and user.card number is borrow.card number and user.borrower's name is Vijay. So we found out the titles of all the books issued by Vijay. And here we selected out those names such that the set, suppose this name is Narosa, then select t.sname from sub t where select the title from book where t.accession number is s.accession number. So for anyone whose name is there in the final solution, that person must have, this will give you the title of all the books supplied by that person, and this must contain this relation, this result as a subset. So this will give us the names of all suppliers who have supplied titles corresponding to all the books issued by Vijay. This corresponds to the division operation in relational algebra. We use the division operation to solve this, and we use the for all operation in tuple relational calculus to solve this problem. We also did the existential queries, exists and not exists, where we found out whether the set is empty or non-empty. Today we will do some other additional operations. One is related to ordering, second is related to the aggregate functions, and then we will proceed on later on to do operations which allow for modification of the database, and we will have a quick look at the data definition aspects provided by SQL. So, we will first see the ordering and the aggregate functions, and after we complete seeing the ordering and the aggregate functions, then we will see these two. So, first we come to the ordering functions, and let us take an example. The ordering functions, the language SQL provides certain functions or certain statements which allow us to group and order the resultant relation in a particular way. Let us see this one, which contains the additional statement order by. This says select supplier name from sub where price is greater than 1000, order by supplier name. So, the resultant relation will give you an ordered by supplier name, that is, the final answer will be ordered according to supplier name. Now, it will be ordered in ascending or descending order according to the default ordering of the system, according to the default ordering of the system. Now, before we proceed, I hope we can remind ourselves of the example database which we were doing. The book with accession number, year of publication and title, the user with card number, borrower's name and borrower's address, the supplier with supplier's name and supplier's address, the borrow relation, accession number, card number, date of issue, the sub relation with accession number, supplier's name, price and date of supply. So, this will give us from the sub relation the supplier's name only. This will give us only the supplier's name and ordered in the particular default ascending or descending order. Okay. We could have got more than only supplier's name. We could have got supplier's name and we could have got accession number and order it by supplier's name. So, it will give you the whole thing ordered by supplier's name, but it will give us both the attributes supplier's name and accession number from this, where price is greater than 1000, only these relations, and it will give us the supplier's name. Now, we could order it specifically according to our particular type of ordering. For example, we could say order in ascending order, or we could say order in descending order. Secondly, let us take an example like this. Select star, star means all attributes. Star will give you all attributes. Select star, this will give you all attributes. From book, order by, year of publication in ascending order and accession number in descending order. So, this means that all the attributes of book will be displayed. It will be sorted in ascending order by year of publication, and those books where the year of publication is identical, there it will be sorted according to accession number in descending order. So, this is the primary sort key, and this is the secondary sort key. And this need not be for a particular relation only, we can do it for any relation. This order by is on the resultant relation. That is, we can do a join of two relations and then do a order by on the attributes. This is not meant only for a single relation. This is the simplest order by construct provided. Now we will see the aggregate functions. Normally, relational algebra or relational calculus does not provide you functions for computing minimum, maximum, sum, total, but in any practical situation these functions are extremely useful and often are used more frequently than all other functions. And SQL provides you a number of such aggregating functions. Aggregating functions are which are provided, some of them are the average function, which is denoted by AVG, the minimum function, which is denoted by MIN, the maximum function, which is denoted by MAX, the total function, which is denoted by SUM, the count function, which is denoted by count. Now we will see how problems can be solved. That is, we wanted previously to find out the largest maximum price. That will come out very easily in queries which we write down now. Let us see examples with some of them. We have the additional statement here, group by. Select S name average price from the sub relation group by supplier name. Now the aggregating functions will be on groups because they are aggregates. Average is an aggregate of a set. So that set will have to be defined by a group definition. Now this means that it will print out all supplier names and the average price of the books supplied by them, because you are grouping by supplier name. Therefore the average will be taken over supplier name. The average will be taken over supplier name. So this way we will get out all the supplier names and the average prices of the books which they supplied. If we want the total, the maximum as well as the minimum, then we will write down something like this. Select S name sum price max price from sub group by supplier name. So it will return you the name of the supplier, the sum of all the prices, the maximum of all the prices from sub group by supplier name. This is what it will do. It will group them by supplier name, total out all the prices. Now you could have taken the average price out as well.
Narosa, so it will give only the Narosa or all?
Now we want to have only Narosa's price. The question is that suppose I want only Narosa's price, what will I do? In that particular situation, we do not need the group by because we will select out only Narosa. So what we will do is we will say select This name we don't want, we just want the sum of all the books. Sum price. There is no question of grouping here because you will do it on all the elements. You are not going to group them, and you want only one result from sub where S name equal to Narosa. This will give us a sum of all the prices of the resultant relation. You don't have to group by, because there is only one answer to this. This is going to give you only one answer. If you have if in this situation like this, you are returned with a table with a name and a price. So for corresponding to this name you had the price, so you grouped it by this name. But in here you have selected out Narosa, so you need not have the name of Narosa. Yeah, we don't have any of the other. You want, if you want more attributes, if you want sum of 3 or 4 attributes, we will see how we will do. Select title, count accession number, from book group by title. So we will get the titles of books, and for each book we will get how many copies of that book we have got. Now on the group we may have certain questions. Let us say, suppose we want to list out, suppose we want to answer this question. Find out the titles of all books which have more than 50 copies. That is, I don't want the title and their count. I want that this count should be more than 50. I just want those titles. Now we can't put it in the where part, because suppose we did this, select title from book. Now where, what will we do? Where, what? So this question of counting the copies comes after, only after grouping. So unless you first group them, you cannot say anything, and the where clause is not applicable on that. The where clause is applicable prior to grouping. So we will have to first group them. And an additional construct is provided called having. Once we have having, we can write having count of accession number greater than 50. So it will do the aggregation on the grouping of title, and if the count on accession number is greater than 50, only those books will be listed. Now if we wrote here title, would it be correct? It would not be correct, because Here, when you group by title, this title may come once, but depending on the default of the system, you could make it come, you could make it do the actual counting by writing this all title. Like distinct and all we had, select all title will count even duplicates in the group by. So you group by title, and having count, when you write down all title, then it will do the counting even on titles which are duplicates. So effectively it will do the counting on accession number in this particular example. So we could have done this also, this will also work, but logically accession number is fine. In this particular example, accession number is fine, but if you had written all title and group by title in greater than 50, then also you would have got the correct answer. Let us take another problem. List supplier names along with the total number of books supplied by each supplier and the total value of the books supplied by them. We have to list out the supplier names. The names of the supplier, which is S name, with the total number of books supplied by them. So the sum function is there, and the total value from the price, we will be able to get this. So this is a reasonably simple query. Select S name, comma, count. We can put in accession number here because we are going to count the accession number, and we are going to group by supplier name. The total value, so we will sum up the price. We will sum up the price and we will count out the accession number. Here we could have put in all S name also, it would have worked. Instead of accession number, if we put all S name, even that is okay. These three we want.
So here, if you want a distinct function, how do you do it?
We are assuming the default is distinct. From, there is only one relation, sub, group by S name. This is the answer. Select S name, count accession number, sum price, from sub, group by S name. We will take an example. A question was asked regarding distinct, the use of the distinct function here. So we will take an example which tries to answer that question. List out the names of all borrowers, that is B name, and the number of distinct titles of books issued by them. Now the first thing, we will not be able to get this from a single relation. We will require two relations. We will require the user relation to get, we will require the borrow relation to get what books they have borrowed. And that is not sufficient because we are asking questions about titles. Suppose we are bothered only about the distinct books issued by a particular borrower, then it's fine. So let us tackle that problem first, then we will come to this problem. So we are now first tackling the problem of we want the names of all borrowers and the total number of books issued by them. That is what we want. So the problem is to find out the names of all borrowers and list out the total number of books issued by each borrower. So let us see how we will use both the user and the borrow relation. So we will first get the relation, the resulting relation which we want. We will get that resulting relation and then start grouping on the final resulting relation. Select B name, comma, count accession number from user, comma, borrow, where we have to do a natural join. User.card number is equal to borrow.card number. This is how we have got the names of all the borrowers. We have got them. We will group it by B name and count out the accession number. Select borrower's name and we will get the aggregation of accession number whatever on the relation which is formed, and we will group it by borrower's name. The relation is formed by doing a natural join of user and borrow. After we did a natural join of user and borrow, we grouped the resultant relation by borrower's name and we printed out the borrower's name and count. And we could have done many other things. We could have even done this. It would have ordered out the result in terms ascending order of the borrower's name. Order by borrower's name ascending. So it would have ordered out the result in terms of borrower's name. So once now we have been able to find out the total number of books borrowed by each person. Let it, we have only selected out two, this and the aggregate count accession number. Therefore, we will not be able to have date of issue here. So we cannot really order by date of issue unless date of issue is present in the output relation. The question is, if date of issue was here, then we would have had something very interesting. For every book we would have had date of issue, and for every borrower's name we will have this same total count. So if we have Vijay's name 5 times, the same number will come 5 times, only the 5 different dates of issue will come. That is what will happen. because it is grouped by borrower's name, and whatever is the same name, the same count will always be there. If you write date of issue here, then you will get all the date of issues. But if the name in the resultant relation is there twice, these two values will always match, because this is for this name, this is the count. Not that 1, 1, 1, 1 will come because of date of issue. We have grouped it by borrower's name, therefore it will come borrower's name. You can group it by two attributes also. When you group it by two attributes, then whenever these two attributes are same, only then it will do the aggregation. So now let us look at this case. We have grouped it by borrower's name and date of issue. So now for this date and for this name and this date of issue, what are the books issued on that date? This is what will happen in this case. Whereas if this is not there, then it will be only grouped according to borrower's name, and for this borrower, what is the total number which will come? So it depends on what you are grouping by. And if this is here, and you can, then only you can order it, because ordering is only on the output. There is no point on ordering on a function, on a attribute which you do not have in the output. But we will come back to our original question. We now want the number of distinct titles of books. That is, we not only want the books which are issued by him, we want all the distinct titles. So to answer that, we will have to use the book relation as well. We will have to do a natural join of these three and then start grouping. So select borrower's name we have got, and we want the count on the titles. Now if a person has issued the same book twice, do we want that? We don't want that. We do not want, if he has issued compiler design twice, one for himself and one for somebody in another department who wanted the book, or one for his friend. We don't want that. We just want to know how many different types of books he is issuing. So we will write distinct title. This is the example which you were looking for, where you have select borrower's name and count only the distinct titles from. Now we will do a natural join between user, borrow and book, where user.card number is equal to borrow.card number, and book.accession number is equal to borrow.accession number, now we will group. The resultant relation we will group by borrower's name, and we have obtained our result. Select borrower's name, count distinct title from user, borrow, book, where this does the natural join between user, borrow and book. So forget about this aggregation. Select borrower's name from user, borrow, book, where this. So you will get the names of all borrowers who have borrowed any book. And if you want the title here, then you will get the titles of all the books. We don't want the title, we just want count on the distinct number of titles. If we want to find out all the titles, then we will do count all title, all, or count accession number, which will give us the same thing in this particular case. Now we can combine the set operations in the having by part, like we did in the where clause. Let us see this final example. The example is select supplier name from sub group by supplier name, that is fine. Having max price will give us the maximum price of this supplier, because this aggregation will work on supplier name. So max price on sub relation based on every supplier greater than equal to all, select max price from sub group by supplier name. So let us have a look into what this one is doing. This part is giving us, it will give us the maximum price of, it will give us the list of maximum prices grouped by supplier's name. It will give us the list of maximum prices of all suppliers. So for every supplier the maximum price will be here, and this will give us a list of prices. And from here what we want is, we want the supplier name having maximum price greater than all. So effectively this will give us the name of the supplier who has supplied the book of largest value. This will give us the name of the supplier who has supplied a book of highest value. So you can combine the set operations like all along with the grouping operations and solve the problem. So we have seen the additional SQL operations, we have seen the ordering operation, we have seen the aggregate functions, and now we will see something which is related to modification of the database. Till now, whatever we have done in query processing is just to get some answers from the database. That is, we have not changed any element of the database itself. We have not modified the database. The original database is as it is. We have just expressed our questions in SQL language, but none of these questions have actually changed the original database. But in a practical situation, you require modification of a database. Firstly, you require creation of a database, which we shall do last, but in any situation you may require deletion of elements from a database, you may require change of values of elements of a database, and you may require insertion of new elements in the database. For example, when a new book comes to the library, you may need to add that book into the library. When a book becomes obsolete or you start removing books from the library, you may need to change the books in the library. Or a book gets lost, you may need to indicate that this book does not exist in the library anymore. And in some cases where prices may change, or in some cases where you need to change some elements in the database, then we may need to modify some of the values of the database. So SQL provides us certain constructs by which we can do modification of the database. Among the modification operators provided by SQL, we have the insert operator, the delete operation, and the update operation. There are three types of operations provided, namely the insert operation, the delete operation, and the update operation. The second major aspect which is provided in SQL is data definition. That is, how do we define the database itself? How do we define the data relations? What are the relations, the attributes of the relations, and the types of the attributes? And we may create a relation and we may destroy a relation. So functions for creation and destruction of relation are also provided. And finally, we will see what we have is called views. Views are concepts in such that given a complete database, every person who is accessing or using the database need not see or operate on all the elements of the database. For example, a person who is issuing books in the library need not have any information as to which supplier has issued which book, or at least what are the total prices of all the books need not be known to a person who is issuing books in the library. And in more complex situations like a bank, an operator at a particular table who is just entering your checks and giving your withdrawals need not know what is your bank balance. That bank balance will automatically be checked. Whether you are a debtor or how many loans you have taken, you need not know. So views are features provided by SQL so that different persons can have a different look on the database. So we shall see them in the next class.